So this question asks us to think about sodium amide. Is this a suitable reagent to protonate the following compound? And again, what we need to do is we need to think about the reaction. So you have to be able to write down the acid-base reaction. And so this is what we want to examine. Does this reaction proceed more favorably towards products or more favorably towards reactants? And so what we want to do is we want to examine the relative stability of the conjugate bases to figure out which is the stronger acid. Is the acid on the reactant side stronger than the acid on the product side, or vice versa? Well, again, conjugate bases. Let's look at amide. If we look at the atom part, then we have ammonia, we have the nitrogen atom versus the carbon atom. And we would typically say that the nitrogen atom is more electronegative than carbon, so it's better at stabilizing the negative charge. And so maybe we would think that ammonia is the stronger acid. But let's think about resonance. And this is a unique resonance situation with this conjugate base. I can show you resonance in this direction that leads to this resonance structure. And I can show you resonance in this direction that leads to that resonance structure. So I've got resonance going both ways. And it turns out that, in fact, the ammonia is much weaker of an acid than the double, then this is called this proton is at what we call the alpha position. And it's doubly stabilized. The negative charge in this species is doubly stabilized through resonance. So it turns out that this is the stronger acid. This is the weaker acid. And so the reaction does favor the side with the weaker acid. So absolutely, sodium amide is absolutely a suitable reagent to irreversibly deprotonate this species. Okay.